So, good afternoon, everybody. Welcome here. It is a real pleasure having today Professor Angel Rubio here for a seminar. This seminar is intended to be part of the activities of the Dipartimento di Eccellenza della classe di Scienze here at the Scuola Normale Superiore. Just a few words to introduce Professor Rubio. Professor Rubio is a physicist. Is the managing director of the Max Planck Institute for the Structure and Dynamics of Matter in Hamburg, in Germany. At the same time, is co-director of the Max Planck New York City Center for Non-Equilibrium Quantum Phenomena in New York, a distinguished research scientist at the Simons Foundation in New York, and a distinguished honorary professor in condensed matter physics at the University of País Vasco in San Sebastian in Spain. Is at the same time also in the Scientific Advisory Board in the Focus Area of Information at the Karlsruhe Institute of Technology in Germany, and co-editor of a few journals such as PNAS, and as far as I understand, used also to be part of Nanoletters. He has been granted various projects from the German Research Council, the Federal Ministry of Education of Germany, and then he got 2 advanced grants in a row. Probably is one of the few that got that from 2011 to 2021. This year he has been recipient of the prestigious Spanish National Research Prize for his work on computational solid-state physics in Spain. Is a member of the German National Academy of Sciences Leopoldina in Germany and the Berlin Brandenburg Academy of Science still in Germany. Is among the highly cited researchers. As for the research activity, Professor Rubio does many things, but is especially interested in the modeling and the theory of the electronic and structural qualities of condensed matter, develops theoretical instruments that both aid in the study of electronic reactions of materials and molecules, as well as in the prediction of non-equilibrium phases of matter. Is considered a pioneer of computer-aided material science and one of the founders of modern theoretical spectroscopy. In his work, Professor Rubio succeeded in predicting novel material qualities at the nanometer scale, and he also was able to study non-equilibrium phases of matter. And the tools that he develops make possible to calculate electronic excitation of materials and nanostructures. Very recently, he developed the theoretical framework for the quantum electrodynamic density functional theory, which is used to describe the strong light matter phenomena in chemistry and materials science. This is a generalization of standard time-dependent density functional theory that treats time-dependent interactions of protons and electrons. His theories provide novel insights on the changes of the molecular chemical landscape and its reactivity by coupling molecules to quantum cavity vacuum fluctuations, which is also known as polaritonic chemistry. He has also studied other problems. He has worked in the theory of electronic structure of low-dimensional systems, molecular compounds and clusters, and most notably on carbon and more on carbon-nitrogen nanostructures. Today, he will tell us about quantum materials engineering with light, making matter and photons to cooperate. So I will leave the stage to Professor Rubio. At the end, we'll have time for questions. For young students, Professor Rubio speaks and understands Italian, so don't be shy. You may also speak Italian if you like. So please, thank you.
Thank you very much for the introduction. Thank you for coming. And as you see, I just removed, the first thing is a mistake in the title. This coupling is cooperate, no? Okay. Besides all the things that In the introduction, I think I would like to guide you through why this topic could be of interest, and then at the end of the day is to convince you that there is some room using these quantum vacuum fluctuations. Okay, before getting to the topic of the lecture, you might ask why you want to do it, and it's a little bit of an esoteric approach that started in 2014 with one of the ERCs, and then the first thing that came, and this was one of the reasons why I moved to Germany as mass Planck director, is that you come with this idea that can you utilize vacuum fluctuations to modify materials properties, no? And this you will see it in a minute. And if you were going back in the past 10 years ago and ask everybody, can you do it? The answer is no. Okay, and not only no, is that they believe strongly on the no, which means that they will not support you to do it. Then at this point you have to find an alternative way to do whatever you want without the constraint of being limited by what other people think. And this is the ideal place on being both in the Simons Foundation and in the Max Planck Institute. Okay? Then this is the underlying idea. And I hope I will convince you at the end of the day that there is room to do changes, maybe not as many as we wish, but there is something that can be modified. Okay? And that's the whole idea of the talk. Then, before getting there, I will do a small introduction of if this works, which is not working today. Okay. And how to reach these new states of matter that we want to characterize. And then basically, I will introduce you this theoretical framework. Here, you can stop me anytime you wish. And if there is something which is not clear, please ask. I try to keep, except for 2 slides, the number of equations to the minimum. But I wanted to show you at least 2 slides about equations that are connected to quantum electrodynamics theory. Then basically when I do that, then I will basically introduce you 2 examples, both in chemistry and physics. And then that's where I will illustrate the power of the new method. Okay. Then this is the standard approach in quantum materials engineering, but this is not only in physics, it's in chemistry. When you have either a set of molecules or a solid, what do? Either you try to explore how the system reacts to an external perturbation, which is light or electrons, and then you, by looking to the reaction, you understand what the material is doing and what are the properties of that material. That's what you do with spectroscopic tools, no? And this is in all shapes. You can do it in linear, non-linear spectroscopy, and then you can combine those light sources with mechanical perturbations, with pressure, with chemical composition, chemical doping, and so on and so forth. And that's been the cartoon of all those. Then you can do it with electric field, with magnetic fields, and all type of compositions, no? Then basically this is something that will be interesting to change. And then can we add another tool to the modification of those properties? And that's what exactly I wanted to convince you today. You have things, let's make it simple. You perturb your system, you see how it evolves, and in this perturbation, you see all the properties. Now, can I do the same type of physics by modifying the quantum environment? Okay, and let me just do one example that I found was interesting. The idea of the quantum environment, let's take a classical environment. And the question is the following. Can you create a collective motion, a collective behavior of your material by tailoring how the surrounding looks like? Okay? And then you might say, okay, in some cases the answer is yes, in other cases no. Okay, in chemistry is the solvation, that you have all theories about solvation states in molecules, that they play an important role. But in material science, mostly the environment is being used just to control dissipation, to control the coherence, but not to create collective motions. Just to give you what is the underlying idea, let's take one example that I took as an exercise when I was postdoc at Berkeley. That was the time of the World Cup in the United States. How many of you like soccer? The Americans don't like soccer. Okay, they like the American football. Okay, the question is, at that time, if you go to the 94, basically there was this motion of the Mexican wave. on the stadium. And just because the Mexican wave is a typical collective behavior of more than 30,000 people that move in a very low frequency mode all over the stadium. We can do many others, but that's just to give you one flavor of what is a collectivity. And then you might ask why I'm telling you that. And I'm telling you that because if you were at the entry, and this was done by the people doing social science, asking the people that was going to the stadium the following question, which is, are you going to do the wave if some people start to do it? 80 to 90% of the people reply, no way I will. And the other 10% were the guys from Brazil or Mexico, Latin America, that they were coming there for other motivation. No? But there was a clear no. And this is the thing, that what you want to do with this environment is to make the material do what they don't want to do. Okay, and why I'm telling you that? Because if you go to the videos and you see all the stadiums, then let's go to the 4th of July, that was the game Brazil-USA, that Brazil won 1-0. You will see that the Americans are sitting there more completely immobile. And then you have one spot, just in one of the corners. I was in that game. Then that's in one spot, and I was in that spot, which is the Brazilians just jumping up and down, up and down. And then you start seeing that this motion of the Brazilians was just hopping to the nearest neighbor. And then some of the Americans start. And then you reach a critical mass of Americans jumping, and all of a sudden you get the wave. Then everybody behaves the way they didn't want to do, and they stay that way. Okay, that's what we want to do with the materials. We want to change what is your boson fluctuations that will drive the system into another state. If you take this argument, superconductors, superfluidity, any condensed phase is based on how to control those fluctuations. It's not that we know, but it's something that we want to do. Okay? This was more to motivate what we want to do it. And then basically this is what I wanted to tell you. This is more of playing like a theater, which is what basically what I told you before, what we are familiar with. I'm sorry that this is not working. Is that you have in the normal Hilbert space with the spectroscopy tools, you are always, or we are always looking to a corner of the Hilbert space that corresponds to the ground state, the basic properties, and small perturbations of that ground state, which would be linear, second order or third order response. Then you're moving in that small corner of your Hilbert space, because you are treating the external source as just your probe of the system. Here on the spectator, no? What I was telling you. And this basically because you have all the components of your matter are the one that are going to be active, and the external field is the one that is treated just as a probe. And then what we want to do is, now that you have all the external sources, which is your electrons and photons, with the components of the material playing together. No? And this is the new state of matter, which will be a sort of composite new quasi-particle that you are going to use to characterize the properties. Then basically what we want to bring is something like actors plus director. In this case the actors are the matter, the director were the photons and the electrons, that we make them together. And for this to work you need to reach what you call a strong regime of coupling between the light and the matter, or the director and the spectator, no? Which is of the actors. It's the same argument, how you make things interact in a strong way. And then clearly you realize that the right source is this quantum electrodynamics approach to treat electron-light interaction. Okay, and then this was the introduction, and I will now bring you, this is the question that I hope we can answer today. Can we use cavity-enhanced vacuum field fluctuations to modify and control materials properties? This, I was biased with the reference. These are the ones of the group, but there are many other people that has contributed and is contributing. Marco is contributing recently in different aspects of it, even in putting important constraints about when it should not work, which is true. Then it's not a question that we should not be aware that under many conditions the effect will be zero, but the question is under which conditions is non-zero. Okay, and let me just give you another example that these fluctuations play a role. I don't know how many of you follow these gravitational waves and the way they were measured. The way they were measured with this precision of 10 to the minus 20 is based because you use a squeeze light and you just measure the interferometry of the quantum fluctuations. Without quantum fluctuations, you will not be able to do those experiments that they did in LIGO. Okay, then it's something of those interesting things that is connected to the fluctuation of the electromagnetic field in light. And then this, okay, you can see how is this experiment being done. You have these tons of material being moved by 10 to the minus 20 meters. And that's what you measure in those interferometric experiments. Okay, that's to give you that there is an effect. But then let me just give you the questions that I would like to answer today is, can we modify the electrical conductivity due to the vacuum photons? Can we increase the transition temperature of superconductor? Or can we increase the topology or any phenomena of a molecule or an extended system in the cavity? That's the 3 questions, but you can add many more that you might dream of. Okay. Before getting, let me do an idea of what we are having in mind. If you take 3 quantities, which is the interaction strength, the electron correlations, and the photon number. Okay, this interaction strength is the light-matter interaction. Electron correlation is what everybody likes in condensed matter because you like to work on correlated materials. And then the photon number is what you do in classical field is weak photons and strong field physics. This is the present Nobel Prize in Physics on attosecond dynamics and strong field physics, which is happening in this case. And then basically most of the systems that people do look is in the linear response on higher order with weak photon numbers, which is this corner. This is what many people do. And then you can go to a strong exciton polaritons, when the light matter coupling is strong, or the cavity QED, which is in this regime, but still the photon number is weak. And then you can combine that with high harmonic generation, or what is called a mode insulator of light, when you have strong correlations and a strong number of photons. Then you can move it on the other side, which is cavity quantum Hall effect, when you have strongly correlated systems, which is the fractional quantum Hall, but interacting with light. And then you can categorize where you are in the corner of your interaction. Then you play with those 3 type of interactions. Okay, then this is so much. This is what we want to do. And then I get to the point is we want to utilize the 0-point energy of this type of setup, which this is a cartoon, but then let's put numbers, because I think the first thing you want to know is how big is this density of states of the vacuum fluctuation. The first thing you realize is that there is 1 over c to the cube, which makes this number to be quite small. Okay, then let's put numbers, and then just that you don't think that I'm trying to lie to you. Okay, let me just skip this one, and then maybe we go later. Let's take two cases, which is the Lamb shift, that maybe you know, is that how is the splitting of the 2s and 2p orbitals of the hydrogen atom as a function of the coupling to the vacuum field, just the vacuum fluctuations. Okay, this was the Nobel Prize a few years back, okay, quite a few. And then you can see that the splitting of those levels is 10 to the minus 6 electron volts. It's small, but non-zero. Okay, and this is if there was no vacuum fluctuation, those 2 states will be degenerate. That's just to give you. Then let's go to the other extreme case and forget about van der Waals, because it's another way. Casimir-Polder forces, which is a clear example of 2 metals being attracted. And this is just coming because you have standing waves in the cavity, and this produces the attraction. For those of you that have not studied QED, for those of you that have studied QED, you know it very well. For those of you that did not, this is an extremely tricky thing, because we think we understand it. Okay, I think we do, but not so well, because this is one of those examples in physics in which for each cavity mode, the force is repulsive. For all, for 1, 2, 3, 4, any. And the sum of all is attractive. Okay, then this is something that it's one of these Riemann sheet sums that you have to do to integrate the summation, and you go to the first Riemann sheet, and this will give you this attraction. Then it's a tricky thing to get the right things, and this renormalization is what gave Feynman the Nobel Prize with Tomonaga when they did the renormalization of the QED. Okay, that's what we are going to play, but if you see the numbers are really small, okay, then we need to see how to increase those. Then let's jump to another case that is known, which is in quantum optics. This is what I just told you in a minute. Is you have the ground state, you have the material excitation, you come with the photon field, which is here. Then basically, if it's resonant with this material excitation, you will form a bonding and anti-bonding state, with the splitting is proportional to the dipole moment of the material, and it's 2G. Forget about that. But this is of the order of 10 to the minus 6, what I showed you before. Then it's a very weak effect, and this is what is called the polariton, the lower polariton and the upper polariton. Okay? The question, can we increase that splitting? And this is known in quantum optics. If you put many of those dipoles, non-overlapping, but in a cavity, you have any of those, it takes you 2 lines to prove that you get lower polariton and an upper polariton. The distance between those two goes with the square root of n, which is the number of dipoles. But then you have many, many, many dark states in between. Those are the bright states, the lower polariton and the upper polariton, and the other ones are dark. Okay? And this will be the collective motion of many dipoles in the system that could give you decay superradiance and many other phenomena, which is interesting. However, in solids and in molecules, what we are interested in is in the regime in which there is overlap between the molecules and there is no linear couplings between those. Otherwise, the phenomena will be small and irrelevant. Okay, then to summarize, the thing that you have to take home, and I will not show you, is that the coupling of the light matter scales as 1 of the square root of the volume. We can discuss what this square root of the volume is. I'm happy to do it offline because it's a tricky thing, but it's not, even in the thermodynamical limit, you can prove that this coupling scale, when you include all modes, is finite. Small, but finite. The coupling is collective. Then if you have many of interacting dipoles or an extended system, will go as the number of particles, a square root. And then something which you have to keep in mind is that all those quantum vacuum fluctuations, on average, the electric field is 0, then there is no real electric field. In the cavity is the fluctuating field, E squared. Just remember that, because I think will be important for what I'm going to tell you that. Because one misconception in this field is that people think you have to couple to IR active modes or dipole active modes. No, you need to couple to E square active modes, which is Raman active modes or second order processes. This is important because in the linear regime, the effect on average will be 0. Okay, this was all much for the introduction. And then the last thing on the introduction is what you can do with these cavities if you believe that there is an effect. Then you can have the standard work. I am guiding you with the standard mirrors, which is a mirror, and then you have linearly polarized standing waves with the polarization in the plane. No? This is the standard thing that you know. And those are the standard linear polarized. Then you can have helical modes by having Faraday mirrors. And then you have something that is moving this way. And when it reflects, comes the other way around. In that case, that system is helical, but you don't break time reversal symmetry. You have 2 modes, the left-handed and the right-handed. Okay? You can be a little bit more ambitious if instead of having vacuum in between the mirrors, I put a birefringent material, I will have a difference between the propagation of the left and the right-handed. Then if you look to that, one of the birefringent materials is sugar. The one that you put in coffee is the best birefringent. It's something that experimentalists would not like to put in your mirrors because it will destroy everything, but it's perfect because the splitting of the left and right-handed is very large. But then if you compute the modes, what happens is in one area of your cavity, you will have perfectly left-handed, and in the other area, you will have right-handed modes. Which means if you are beyond the dipole approximation, or you can do it in the torus geometry, and you put graphene, for those of you that know graphene, and you plug it in the position of the left-handed or the right-handed and not in the nodal structure, you will go from a system that has a gap and is a semi-metallic system to a system with a gap. Okay? Then basically you make, just by placing the graphene in one of the positions. It's a little bit surprised. The gap is really 10 to the minus 6, then will not be a real gap because it's so small that even 0 temperature effects will close it. But formally, you have you go from semi-metal to a topological insulator. As long as the coupling is finite, the gap is proportional to the coupling, which is 10 to the minus 6. Anyhow, then this is the idea, and then let me guide you how we are going to study that, and then these are the questions. Okay. Then the first thing is, you will say, okay, we already, and many people have told you, have problems with the many-body problem. We know how to solve one electron, two electrons, and an homogeneous electron gas, which is infinite homogeneous electron gas because we know the solution is a plane wave. And in between, we have to do something because we don't have the exact solution. And then there are two schools of thought. One is the many-body scheme in physics, or the people doing coupled cluster or quantum chemistry approach, which is, let's take the full Hamiltonian of the system and do an expansion of the many-body wave function, and then by adding more and more terms, I will get eventually to a converged solution. Then this is how to solve the exact Hamiltonian the best you can with an expansion. Okay? This is one way, it's extremely valid, and is what we are going to use as reference. But this scales extremely bad. Then you have coupled clusters, CI techniques that you can do for very few number of electrons. Imagine if now you add bosons to the thing as photons, then it's basically impossible to solve exactly. Then the other school of thought is what is called density functional theory. In density functional theory, what you do is a mapping of the interacting system into a non-interacting one. And this mapping is in principle exact, but this in principle is very big. In principle, we don't know it. Then at the end of the day, what it entails is that we will have an approximated Hamiltonian that we know how to solve exactly. In the limit of having the exact theory, the two methods will give you the same. But in practice, they don't. The advantage of DFTs can be scaled to large number of electrons, large numbers of atoms, plus I can include the photons. And that's what I'm going to try to tell you today. Okay, then this is the path that we are going to do. And then to give you the glimpse of the physics, how we do it, is you have electron-electron interaction, no? And then you have electron-photon. And when you go to quantum mechanics, you always teach, we teach quantum mechanics in the Schrödinger picture in which we look for stationary solutions, which is H psi equal E psi. And then you do the minimal coupling. You change P minus EC to include the external electromagnetic field, whether it's classical or quantum. This is a valid approach. But who told you that quantum mechanics is stationary? It's your decision. Because you can find another gauge in which this is not the case. Then it's a question of defining where you want to work. Okay? Okay, then let me tell you why I'm saying that. You can think from particle physics, the interaction between electrons. The interaction between electrons is you have one electron coming here, another here. There is an emission of the mediator of the interaction, which in quantum electrodynamics is the photon. Then a photon is emitted, takes a time to go to the electron, is absorbed, and then re-emitted. And then by exchanging of the photon, you have the process of electron-electron scattering, and electron-electron interaction. But then you see that this process is a time-dependent process. It's a scattering process, as all things in QED. Quantum electrodynamics is a scattering theory. Then, but this is compatible with the static picture that we have of the electron-electron interaction, how this come about. Then in this time-dependent phenomena, which is the one I'm going to use, everything goes as the currents interacting with the electromagnetic field. It's a linear interaction, and I'm going to do the density functionalization of this Hamiltonian. But if I do a gauge transformation, because this is a temporal gauge, and I go to the Coulomb gauge, I can prove that the longitudinal part of this interaction gives you the Coulomb potential. And then the transverse parts give you the standard retardation effects that you have in your electromagnetic field. Then it's not that the two theories are completely different. In one case, you are looking to the stationary solution when t goes to infinity, and in the other case, you look to the eigenstates, so your Hamiltonian that give you the same point in space. Then you can reach them by solving this in time or by diagonalizing the problem in R prime. Here is a linear problem for those of you that know how important it is to have a linear problem because it's easier to solve. And this is a two-body problem that we don't know how to solve. And this is one of the open questions in principle, which we still didn't solve, but if some of you have a solution, I think will be extremely important. In the temporal gauge, you only need the one-body density matrix to solve the problem. But it has to be the one-body density matrix of the electron and photons. which is unbound because you don't have quasi-particles. Instead, in the two-body case, you need the one body and the two-body density matrix to get the energy and the quantity. Then you have to decide which. We take the first one, and I'm not going to give you all the details. What you have is something which is important that you might have realized. I'm going to work in the non-relativistic or semi-relativistic limit, and it will become clear in the following. I will prevent the system to create electron-positron, and that I will remove. I will remove the Dirac-C. For material science and chemistry, working with 500 mega electron volts is irrelevant, then better to trace them out. Also, because if you want to include them, the theory is not bound from below, then we have a problem to define a variational principle. Okay, then I take the non-relativistic limit, and at the end of the day, your Hamiltonian has the kinetic, the Coulomb interaction, the interaction with your electromagnetic field, and the matter Coulomb interaction, which is, I just keep here the transverse part because the longitudinal part is being transferred here. Okay, why I did all that, I'll tell you, and this is the only thing you have to take home. This is, the mathematicians, I got a surprise, they love this Hamiltonian, the real mathematicians. They say that is the only thing physicists we do right, because most of the things we do wrong, according to them. And is this thing that is a real self-adjoint Hamilton operator, is bound from below. This is really important, because otherwise there is no solution. And there is one problem that has an ultraviolet cutoff, as all theories in QED. But this boundance from below is extremely important, because then you have variational principle. As we teach, the Schrödinger equation is the variation of the energy with respect to the wave function, give you the Schrödinger equation. The variation of the energy in the Pauli Friis Hamiltonian with respect to the wave function, photon electron, give you this Schrödinger equation for the Pauli Friis. And this is self-consistent, and you can solve it. And on top, the mathematicians has the proof that there is solution of that Hamiltonian. It's a non-trivial statement, what I'm saying, because for many things they have proof that they don't know if there is a solution. Okay? Then said that, that's what they like. What you can do is take the standard, for those of you that don't know it, but so I apologize, is to prove the density functional theory. You have the full Hamiltonian, which is this is the electron boson wave function. You don't need to know it. And this is the only thing I want you to take home. The many-body interacting wave function is uniquely defined by the current operator, which is a three-dimensional quantity in time, and the transverse part of the electromagnetic field. You only need to have two vectors in space and time to describe an full interacting many-body system. Okay, this is good to say, but we don't know the functional. Then, okay, then we are fair. But at least this is a proof of concept, and that's what we call quantum electrodynamics density functional theory. If you want to translate it to your language, this is equivalent to say that you have a self-consistent coupled Maxwell-Consham-Pauli equations, which I'll show you in a minute. And these were the two equations I wanted to show. Is that the Schrödinger equation for the electromagnetic field has the kinetic energy of the electrons, of the ions, the interaction, and these effective fields, they just come from the electromagnetic field. This is the cavity field plus the induced by the matter. It's a self-consistent field, and then that you need to solve. And then the interaction goes with this effective field. And then on top of this equation of motion that gives you the Schrödinger equation, you have Maxwell equations, which is, I wrote it as a second-order differential equation, but you can have it the way you like. Okay, which is with the current that is the generator. Then you have a self-consistent process between the current generated by the matter. This is nice because it's an n-body photon Maxwell equation. This is new because, at least for me, every time we teach Maxwell is for single photons. This is for n photons that are interacting. But looks exactly the same as the single photon wave function. Okay, and that's what we have to solve. Then I will not give you the tricks. There is a way to make this looking exactly equal like that, which is the Riemann-Silberstein transformation, and then you can solve it in the computer if you have a solver for the Schrödinger equation. Okay? Then just to summarize, this is what you do in a standard density functional theory. You have a potential to many-body wave function to density, and then you solve this Schrödinger equation, which is a one-body Schrödinger equation. In what I told you of quantum electrodynamics density functional theory, you end up in the set, in the same equation, with an external potential that has an additional term. That is the change correlation potential due to the electron-photon interaction. And that's what we need to get. Okay? That's the analogy. Then the price is that this part, for the electronic sector remains as unknown as was before for the electron-electron interacting. Then you have to bear with me that everything I will show you now, this is not problematic. Okay, and I choose systems in which this is not problematic. Then, but that's the approach. Then, if you don't like it, I'm happy. You can put here coupled cluster or anything you like. The theory holds equally well. Then it's just how to treat the electron-electron part. Okay, and then you might ask, Angel, how then you tell us that, and how do you get the potential, this exchange correlation potential? And then this comes, physics comes to save us. If you have many photons in vacuum, photon-photon interaction is extremely weak. One photon with the other interacts with 1 over c squared. It's really a relativistic interaction. Then in the non-relativistic case, photons are bosons that are independent particles. This is ideal, because everything that is independent we know how to solve. And then the light-matter coupling, as you saw, is not very strong in general. It's weakly in that energy scale. Then you expect that the functional of photon electron will be well described by treating photons as independent particles. And this is perfectly suited for quantum Monte Carlo. You can do what people did in the electron-electron interaction, which is I have an homogeneous electron gas of electrons, and I have an homogeneous electron gas thread by photons, which are not interacting. And that one I can solve in quantum Monte Carlo, because I know the wave functions, and I can do a solution. No? And that's what we did. And in that case, just to give you a story, there is a solution that gives you something that, for those of you that know density functional theory, this will sound familiar. For those of you that don't know density functional theory, it will be a magic. But at the end of the day, you get a potential for the exchange that goes with the density of the system to a power and all the gradients, which is basically coming from the current operator. And this is quite, because it's analytic, it's with the sum over all modes of your cavity. And this is basically an analytic expression, which is the local density. Then, just to give you where we are, if you go to 65, when Walter Kohn and Sham proposed density function theory, the approximation they gave is the local density approximation. And then 65 was what they proposed. At that time, the local density approximation for electrons was not good enough, and they have to wait to the GGAs that were 20 years later. And then if you put scale, then and after another 20 years, they got the Nobel Prize. Then that's. I'm not going to say that we get to that point, to the last one, but we are as they were in the 65. Okay, this is the LDA for photons. And we have already done in CCQ the GGA. We already did that, but we need to go steps beyond. Okay, what I will show you is everything done with this functional. Okay, good. And then probably, if I'm talking too much, let me show you one case, because for many of you, some of you already saw this movie, but it's just how it looks like something that you are familiar with. You all know Fermi's golden rule, and the fact that if you have an excited state, there is a spontaneous emission. Then there is a natural line width of a given state. How do I get that from my theory? No? You can solve it in perturbation theory, but then I'm going to show you how it looks like, such that you get an idea of what those fields look like. Then I have an atom in which I excite, and then I will look to this process. No? The electron decaying to the ground state and emitting a photon. Then this is the initial condition. I have the population is 1 in the excited state and 0 in the other one. Okay? And then you will see now the dynamics, and I hope I will be able. Then immediately the photon is emitted. You recover the Lorentzian line shape. See how the electric field looks like, because the electric field is unobservable. It's being absorbed. You get a tail. And every time you get the photon absorbed, there is the probability of the photon being absorbed, which is proportional to the dipole moment. You get it here. And then if you look to the right, you see that it takes some time for the line width to be formed. It's being distorted on the time scale of the velocity of light. And then you can keep going this. This is, of course, don't forget this is at the speed of light. Then we are talking about really, really, really small time scales. But this illustrates that you have access to the standard Fermi golden rule, which the absorption is proportional to the dipole moment, the formation of the spontaneous emission, which is the line width, and you have access to those quantities. And now, if you have access, you can immediately try to control those properties. Okay? Okay, this was basically what I wanted to tell you. We can do it with 2 photons if you want, because this is what I have here in the, and then you can get bound states in the continuum, but this was a little bit irrelevant now. Let me give you 2 cases of applying, because otherwise we will not see it, which is chemistry, and then on materials I will ask you which one you want to listen to. Okay? Then chemistry, let's start with something that at least you will not debate is correct, and then we can go to something that can be a little bit more that you can argue. Okay. The first thing is energy transfer. Energy transfer, and then you might tell me that I'm trying to bring you away from my main argument. This is not a ground state property, because what I do is I have a molecule which is a donor and a donor and an acceptor. I excite the donor and I see how the energy from the donor is being transported to the acceptor. This is what happens in photosynthesis and in many chemical reactions. But this is an excited state property. However, this is one of those excited states that has tremendous applications all over. It dictates how plants work, how our body works with the light, everything that is reaction center and absorbing center, how you have to monitor. And then the question is how I transfer this energy over long distance, because usually this is the case as 1 over r cubed or r6, and then only happen in few nanometers, but you want this to happen over larger scales. Nature has done some tricks in light harvesting complexes with the distance for the energy transfer is much larger, but this is connected, we can discuss it later. How about a network of porphyrins? Also in practice in quantum optics you do optical fibers to connect different emitters, but the question is, can we do it more in a natural way? You have the donor and the acceptor. What happens if I use a mediator that transfers the energy and then makes this decaying of the energy transfer, which comes from the longitudinal part of the field, not from the transverse, being irrelevant. Okay, that's what we did. And this is a Gedanken experiment. It's not something that can be done in you can do this in the computer, but not in experiment. Because the gap here is around 5 eV. Then a 5 eV cavity is impossible. If you do the analysis, it's too small. But in the computer we can do it, even is better, because then we have less volume. Then what we are going to do is this exact solution of the problem of the donor acceptor, and then I want to see how is the energy transfer when I excite this from the HOMO to the LUMO, and I look how the acceptor is being modified. This is nothing else than you have a dipole fluctuating here, and as an antenna will induce a dipole here, and then you have this dipole-dipole interaction. This is the classical argument. Then let's go to the plot. If you do the classic, which is basically no coupling, you get the power load behavior that as a function of the distance, the energy transfer goes to 0 very fast. If you do it now with the quantum photon in the cavity, with all the Qs, but tailored to that frequency, you all of the sudden see that there is the longitudinal part that will be basically indistinguishable from this one, but there is one component which is the transverse part of the electromagnetic field that dominates the energy transfer. And that one is constant over many. Eventually, if you keep making the cavity long, it will go down. Then it's not forever, because there is retardation. But up to 60, even more than that is difficult for us to do the calculation. Then you see that it's more or less constant. This is nice, but it's not a ground state. Then I just wanted to show you another case, and then I stop in chemistry. Let's take one of the famous reactions in chemistry, which is Diels-Alder reaction. This is connected to the previous 2 Nobel Prizes in chemistry, which is the click chemistry and the organometallic chemistry. It's how to activate chemical reactions for pharmaceutical companies. Those are really important in all products related to cosmetic, to creation of pharmacs for our everyday life. And it's really important to be able to separate the 2 enantiomers. You might have heard that one of the problems in bio is the fact that one of the enantiomers usually is acting the way it should, and the other is acting the way to kill you. Then better you take the good one in many aspects. Okay, this is not the case for this reaction. This is reaction related to a chemical process, and then the thing is that you have this endo and exo transition state, which is basically the only difference between the two is whether the CN bond points to the left or to the right, which means whether the dipole moment is this way or this way. Okay, That's the whole idea. Then you might ask why I'm telling you that. Now comes the good thing of being theoretician. I assume all molecules are aligned. Okay, then a big assumption. The chemists do not like that assumption, but let's assume all are aligned. And now I have a knob, because I can put the polarization of the cavity along the dipole or perpendicular to the dipole. Okay? And then I can see what is the effect. Then that's exactly what we are going to do. What happens if the cavity is polarized along or in the other direction? Okay? Then I will not guide you through the equation. What you can compute is the initial state, the final state, and the transition state. But what I wanted to show you is this curve, which is more the situation. If you go in the different directions of the polarization, which corresponds to whether the molecule, the polarization of the cavity is along the CN or not, you can really get that the endo is the major product, or you can reduce it to 0 if it's in the set direction. But in the other case is the one that will dominate. Then you can change which of the two isomers will be dominated in the chemical reaction. Okay, you might ask, oh, you solved the problem. Yes and no, because if you go to realistic values of the light matter coupling, the realistic values are here. Really here, they are very small. Still, you have some selectivity, but we need to increase the light matter coupling to make it really practical, no? But this is just to give you that in principle, if you have a way to increase the light matter coupling, you will have sort of selectivity in this enantiomeric selectivity. Okay. Then let's move to the materials, because in materials there is an intrinsic enhancement by having many dipoles. And now, okay, how much time? It's 10 minutes, no? Or 5. Okay, now comes. You want ferroelectricity, magnetism, or superconductivity. I have the 3, but I cannot do the 3. Then I don't know. You don't care?
I would vote for superconductivity.
You vote for him? Okay, superconductivity. Okay, then we skip. Okay, it's not a problem. I just skip ferroelectricity. But only just on magnetism, let me just give you one thing, which is interesting, because although he didn't want magnetism, okay, let me tell you why magnetism is, I think, is interesting. Magnetic materials, you can have this antiferromagnet. Okay, let me just show you. This is a typical two-dimensional ferromagnet, which is ruthenium trichloride, is antiferromagnet. But the beauty of this antiferromagnet is that it's an insulator. Okay, and then let me just guide you. If it's an insulator, the cavity mode will penetrate. Then it's not that if you have a metal, you have to look for a cavity frequency such that the penetration length of the field is larger than the material. Otherwise, the metal will act as a screening, and then there will not be cavity effect. Then if you have a perfect superconductor, you have to tune the cavity frequency to the gap. You have to look for a place in which the system is transparent, in a way or another, to make this argument that I'm telling you practical in experiments. For the theory, it's not a problem, because we can always assume that the field is inside and then what is happening. But that's just for practical purpose. Then this is what people is now trying to do in the experiments for ruthenium trichloride. And the reason you might ask why is interesting. Okay, it's interesting because people think it's a quantum spin liquid. But for me, it's interesting because the ground state is an antiferromagnet, zigzag, and very close to a ferromagnetic transition. Then what you can prove is that the cavity will induce this antiferro to ferromagnetic transition with basically the standard light matter couplings that you have. Okay, this was the take home, which is what I wanted to show you here, and we skip it. Okay, and then let's go to superconductivity, and then we finish. Okay, but the magnetism may be, if I'm not mistaken, the people, Eduardo, Baldini, and Juncono, and Jerome, they finish the experiments, will be the first evidence that of cavity-mediated modification of the ground state of a material, which is not the 2D electron gas, that they have already proven in some way that things are modified. Okay, superconductivity, you have many proposals, and one of them is something that Marco has worked on that it should not work, but I will tell you anyhow. Is you can use or you can think of coupling the cavity to a standard BCS superconductor, which is an electron-photon-mediated pairing. Okay? The other thing, which is more what people wanted to do, is some sort of ampere coupling, whether I can induce electron-electron pairing by having the quantum field of the photon mediating the interaction between electrons. This is what is, the effect is non-zero, but it's so small that it's non-practical. And that's what Marco has demonstrated. And I think this is a good example of this ampere instability that it might not be realizable. And then there are other proposals with non-equilibrium phenomena mediated for the inducing pairing. And this, as you are students, was one of the things that was fun, because this was started in 2017. I asked Mikhail Sentev, that was my postdoc, to do this calculation. Okay, and then now comes what, before getting to the data, I told him, let's do it on graphite, the intercalated graphite, anything that is simple, aluminum. Choose a typical trivial BCS superconductor. Okay? But if you ask that to a student, the first thing they tell you, this is boring. BCS is from the 60s. No one cares about BCS. We need to do highly correlated electron-mediated superconductivity. And then you have to find a compromise between those two. And at that time, in 2017, the iron selenide superconductors appeared, which were the monolayer of iron selenide on top of strontium titanate. And this was a correlated system mediated by an interface phonon. Okay? The worst case for a theoretician, because you don't know what you do. But again, let's do it. And then we did the calculations. And all of a sudden, we got what I thought we were going to get, is that you can induce electron-phonon is enhanced. But when you run all the calculation up to the TC, the electron-phonon is enhanced, but the phonon frequency goes down. The TC is proportional to the phonon frequency multiplied by the electron-phonon coupling. The product remains the same. Then it's a beautiful paper in which we conclude that there is no effect in the TC. Okay, you get an effect in the electron-phonon. Okay, this was here. It's interesting because you can prove that the electron-phonon is very strong. You couple to these hyperbolic phonons. It's really nice. You can see it. But then, lesson to be learned is let's do easy things first. Okay, but then we did the easy things now. Okay, and then let's take the one that also Marco knows, which is a BCS high TC superconductor that no one debates is electron-phonon mediated. There are not too many cases that you might think, besides aluminum and copper and the noble metal. And one of those is magnesium diboride. The other one is things of intercalated graphite. Magnesium diboride is a simple material, it's layer, and this is just basically calculations that were done. You have two gaps for the superconductivity, and what you need to know is that the TC is close to 40 Kelvin. Then it's a high TC superconductor. And this was a very large hype in the 80s, because you say if you start with 40, if you do something, you might get to room temperature. Yes, you can do pressure and all that, but you don't go to room temperature. And in fact, everything you do goes down. The TC goes down. Okay, and this was forgotten. But then the idea is, okay, let's take this system, which is simple. It's very well understood. The calculations, if you compare with experiments, are one on top of each other. You have two Fermi surfaces, and there is the nesting between the Fermi surface, which is a Raman active mode, which is a E2G mode. That's just the only thing you need to remember from MGB2 is that. And then comes what resonates. First is Raman active, then will be easy to couple to the cavity. It's close to the sun center, then it's also good for the calculations because we can approximate it with a sun center phonon in a supercell. And that's basically what we are going to do, is to put the magnesium diboride either this way or perpendicular, which is a little bit artificial. Then we'll have the out of plane or in plane. We will include all in-plane modes to restore the symmetry, because everything I showed you before was only for a single mode. And then basically we are going to look for the electron-phonon coupling. Okay. Before getting into that, I think this is for Marco. What we did is the standard electron-phonon calculation you do, okay? Which is we assume that electron-photon coupling matrix elements are exactly, you can compute it with the density function and perturbation theory, and we are going to plug those electron-photon couplings in the Lie-Sverre theory, the standard Lie-Sverre theory. Okay? The approximation there is that we have not derived yet the Lie-Sverre theory in the cavity. And there is not yet that derivation. Then I'm applying everything and putting those numbers into an Lie-Sverre theory which is outside the cavity. Okay? And this is to get the TC. But the electron-photon coupling is computed inside the cavity. Then basically what you can realize is that when you put the system in the cavity, the in-plane and out-of-plane, there is a small, really tiny, this is 10 to the minus 5, redistribution of charge density within the bonds and in between the layers. Okay, let me highlight what is the effect of the cavity, and then this is what you will see. If you are good for the electronic structure, and you look carefully between the red, the black, and the blue, you have to be very good to see a change of the Fermi surface. Then basically, really, you have to really blow it up. The change of the electronic structure is marginal. And this goes, I don't know, Giacomo, what you found also for silicon, that the renormalization of the band gap and all these electronic states in a scale which is 10 to the minus 6 is negligible. Then the electrons are not being modified. Now basically, there is a minor thing, but there is a slightly thing. And the density, what happens when you go to the phonons, and this is very interesting, most of the phonon, if you look, they are not modified. And here I just really did a highlight because this color is for a strong light matter coupling, except this area of the E to G modes. And those are the ones that couple strongly to the cavity. Okay, and then let me, for those of you that remember, for graphite, intercalated graphite, for MgV2, and for many of the superconductors, there is this soft phonon mode that is the one that when you move the layers or you apply stress, goes down. In graphite goes by 100 centimeters minus 1, and is the one that does the coupling in lithium intercalated graphite. That mode is exactly this mode in MgV2 and in all two-layer materials. It's what in the community of intercalated graphite, they call it interlayer modes. And it's something that is being affected by that. And the energy changes a lot. And why I'm telling you that? Because, you know, the frequency will go down. And this is a standard BCS superconductor. And if you go to your BCS textbook, the TC is proportional to the frequency of the phonon mode and exponentially to the electron-phonon coupling. Then you have already one term that is giving you an enhance of superconductivity. Now, if the lambda increase, we will get another term. And the beauty there is that it's not a product, as in iron selenide. One is exponential, the other is linear. Then maybe you can have an enhancement if you get the electron-phonon coupling enhanced. And here what we know is now is what you see. Okay, this is too large, but this was only for you to see it. You see this is over nearly 100 centimeters minus 1. In reality, for realistic couplings will be around 10, 20, much smaller. Okay, then this is what you need to take home. If you compute, this is the electron-phonon coupling compute outside the cavity with all phonon modes, and then you get a lambda of 0.6 to 2. Just remember that number. When you have the out of plane, you get a slightly increase, but it's marginal, of 6.3. And then when it has the in-plane, which is the NGV2 parallel to the mirrors, you get a much larger increase of the electron-phonon coupling, which is 6.8. And there is a region of the phonons that are this 2G mode that is basically the one that is responsible for the electron-phonon coupling in hands. And then let me plot it in a completely artificial scale, just to show you that this is as a function of the light matter coupling and the frequency, this increase and saturates. Okay, this is for the out of plane. And you can go from 0.6 if you want to 0.9 in the case of one, but this is completely unrealistic. Realistic light matter couplings are here. Okay. Okay, and this is basically how the electron-phonon coupling, what I show you, spreads in the different configurations, which is this part that gives you the contribution. Then you can do the same analysis of the electron-phonon coupling. And now when you plug that in your TC, then forget about, this is all the matrix elements dependence. What you get is this wonderful plot that outside the cavity, which is the black, and then if you are out of plane or in plane, you can go up to an increase of few Kelvin to 10 Kelvin increase of TC. Okay? This is for strong to ultra strong coupling, 10 Kelvin. Even if you just reduce it by a factor of 10, which is 1 or 2 Kelvin, I think will be more than enough to prove that there is an effect. Okay? The only problem here is experimental. If you take the optical absorption of molybdenum of manganese diboride, the Drude term is extremely wide. Extremely. Then it's nearly 0.5 eV. Then you need to put the cavity mode above, or do the following, which is the trick that we are doing now. Okay, the experimentalists are doing now, is instead of doing superconductivity on the bulk, doing it on a thin sample of 2 to 3 layers. The TC of a 2-layer or bi-layer magnesium diboride is not 40, it's 20 something, but still is not negligible. But with 2 layers, the cavity mode penetrates, then the theory will be applicable. Then now I don't know what is the outcome, but soon we will know the experimental results for this particular case. Okay. Then clearly, this is the end. Then we have to go beyond the dipole approximation in many of the cases that I show you. Don't forget that, okay, maybe I forgot, my cavities are perfect. I didn't include the leakage. We have to include the leakage. And this is really nice because then you can come with light in and light out, and then look what is happening. And you can use that as your spectroscopy tool, the in and out. No? But also this introduces a dissipative channel that will destroy the coherence that you have set inside the cavity. Then you need to know whether this is so strong that the effect I told you will disappear. This is something to be explored. Then, which is what I told you, the inclusion of temperature and losses. And then if all that works and survives, which I think it does, because some preliminary data indicates that there is an effect, then we can go to out of equilibrium. And why I'm telling you that? Because you remember the light matter coupling, if you take Einstein relations, is basically we are working with the spontaneous emission term, which is the 1. But usually you have the 1 plus n with the square root, and then you have the n in the Einstein relation. Then if you look, this n, which is the external number of photons, can act as an effective light matter coupling for the whole system. It's what you do with strong field physics. You have a strong intense laser. Then if we just pump the cavity and populate those modes, of course we will increase dissipation and other phenomena that we need to account, but we will have a strong light matter coupling. Then we can move that curve to higher values. Then we can have a larger L, but dissipation. And then we need to find the compromise between the two. Okay, and that's, I think the future will be this case, if you ask me, because this is where you can get realistic light matter couplings and you can control the physics mediated by the quantum fluctuations. Okay, and now for those of you that want to have imagination, which I think is interesting, we don't have yet results, but we are working, is having this moire physics in cavity. And you might ask why, because the reason is, you remember all the numbers. We are talking about light matter couplings of the order of below millieV. Moire physics is of the order of millieV too, in the best case. It's really weak interaction. Then you have light matter coupling, Moire physics, and electron-electron gap opening of the order of the same quantity. Then you have a system which correlations in the electronic sector, light matter coupling, and mechanical deformations are key to define the system. Then there are 3 competing orders. Okay? And now if you are happy with 3 competing orders, you can add the 4th one, which is the rotation, which is also the same scale. You can have things rotating. And why I'm telling you that, I think this is, in my opinion, extremely nice, because if you take this phenomena and you rotate with chiral cavities, as I told you, take graphene. Just for those of you who know, at 0 angle is semi-metallic, but at the magic angle is a correlated system, and the magic angle is very small. This is, if you do this type of phenomena, you will have something which dynamically connect 2 completely different ground states. The question is what it means. And then you can see it as an additional Berry curvature if you were close in the loop. This is an additional Berry curvature in time. And then whether this induces another phenomena or not, this is to be explored. We believe it does, like Thouless pumping does when you translate one material against the other, but this is to be seen. This is more to give you a dream of where we are going. Okay, and I finish. I hope I try, because this is what I like in these days, is convince you that there is a field of cavity, and then you can add it with Floquet. Floquet is the driven case of materials engineering. Floquet materials engineering is not new, has been already there by many years. No? The cavity is what is new. That we have a theory that allows us to treat this in an ab initio approach. You can call it QEDFT, but you can call it QED coupled cluster, QED configuration interaction. Then you choose the two last symbols as you like. Then we'll treat the electron-electron correlation. And then the nice thing is that we can have all these polaritonic condensates that are interesting. And for all of you is that is completely interdisciplinary, in which you have effects of physics on the quantum fluctuations, the light-matter coupling, electron-photon correlations, and connects material science, chemistry, and biology. Don't forget, and now is what the people is doing, that this thing I told you about energy transfer, people in biology are now trying to do this light harvesting complex in cavities to enhance the coupling. It's not that we'll have an application immediate, but this is what they are trying to do with artificial leaves to collect energy. Okay, and with that, this is the list of all the people that has been worked over the last years in the group, and they did most of the work then. I put most of them are already gone, because there is something that I don't know if it's good or bad. Now I forgot to put two of them. Every people that start to work in these years immediately get a permanent position, then they leave the group, and this is not good. This was not the case 10 years ago, because nobody believed it. Then I was able to keep the people for 5 years, 6 years, and this is good because they did the job. But now, after 1 year, they get an offer, they leave, and this is a problem. But anyhow, this is good for them that they get permanent positions. Anyhow, thank you for your attention. I'm happy to take questions.
Thank you very much. I think that we will have many questions.
No.
With this, because we have people on Zoom.
Okay. So you were talking about mirrors, right? Metallic mirrors, but what about polaritonic medium, right? So STO, I can think of it as a polaritonic medium, right, rather than a simple metallic mirror.
I think
are there any qualitative differences between all you said is for metallic mirrors calculations, and that's why you have this 10 to the minus 6 factor? This was the question.
No, what I showed you was for metallic mirrors, because for us it was easy to impose the boundary conditions for the electromagnetic Maxwell equations 0 at the metallic mirrors. Then this is an assumption because we did not treat the mirrors. But now we want to put the real mirrors, real materials, and in that case we don't have that constraint. And in that case, I believe that the metals are not the best ones. Maybe this is phonon polaritons states in which you have a strong enhancement of the near field coupling. Okay, one case is HBN, which you have, but doesn't need to be HBN. Could be any other surface phonon polariton, surface plasmon polariton. They have to be in the terahertz regime, then maybe graphene. You know, you have to work in that regime in order to maximize the light matter coupling that goes as 1 over omega, which is the omega of the cavity, and then the intensity. But I think that's the future, and also because this allows you to go to finite Q, because most of the things I told you was in the dipole limit, but really we need to go beyond finite Q also to have some of the things that are not possible at Q equals 0, which is this the valuation of the concern, you can have it at finite Q, and this is the way to go. But to illustrate everything, I was a little bit choosing the cases in which everything was close to gamma. I kept the modes perfect, and it's an open. Then those polaritons I think are good because they are realistic. You can access the cavity from outside in other region. And if you have the phonon polaritons in BN or in magnesium in molybdenum disulfide for the phonons, you have a perfect reflectivity at the phonon frequency. I don't know if you have seen, there is a paper by Atak Imamoglu on the terahertz regime in which a single layer of molybdenum disulfide has 99.999 reflectance. Then it's perfect. You have an ideal cavity at one frequency, but you have the other frequencies to probe. Good. But we have not done it.
Okay, other? Marco?
I have a question about the phonon and the electron-photon calculation. So
Yes.
you have your DFT that includes the photon field. Do you have like a linear response version of that, or were those calculations done with a finite displacement type?
No, it was done with the linear response version. What we did is we implement this photon-free Hamiltonian in quantum espresso, and also in Octopus so that we have linear response theory. And we did it with linear response for all the Qs.
And like, how does the photon part enter in the linear response?
There is the kernel. When you have the FXC kernel that you use to compute the dynamical matrix, there is one term that is the derivative of the change correlation potential with respect to the density. And if you remember, we have an expression of the photon free in terms of the density.
Okay.
Then you can just do this derivative, you plug it there, and this gives you a perfect case because you can get zero forces for the acoustic branches, then you can relax, and on top you can compute the kernel. You have the potential and the kernel.
Just a quick final question. I wanted to ask, like, is there like an easy physical way to understand the softening of the phonon mode in magnesium diboride? Like, this is like a boson-boson type
Yes.
interaction, right? So I was wondering, like, why would the
We
phonon soften?
physically is basically when you look to there is this dipolar, which is the magnesium and the boron, and then you put a cavity. What you realize is that if you were thinking that as an electric field, which is not, but on average it acts, it'll deplete charge from the bond and distribute it towards the atom, and this weakens the bond. We realize, and we don't know, this is a general feature, that what it happened, and it happens to every 2D material. It weakens the bond and makes the interlayer distance also change. It's an interesting thing because this change of the interlayer distance is something that you could measure experimentally. Okay, but it still is open to... We have not published that because we are checking that is everything. The person that is doing it, you know who is it? It's his student, and it's previous student.
Thanks for the amazing talk. Would you mind spending a few more words on ruthenium chloride?
Of course not. What do you want to know?
The follow-up on having almost two degenerate states. The one is ferromagnetic, the other is anti-ferromagnetic.
Okay, in this ruthenium trichloride, what happened? Let's see if I have it. Just that. Okay, this is how it looks like. It's important for you to know. Ruthenium trichloride is this hexagonal lattice in which you have this antiferromagnetic order in the spin up and spin down channel. Okay, and then I just plot it here. This is sort of when you go to the paramagnetic order, you have a random order of the spins on each side, and then it's completely distributed. No, this is when you close the nil temperature. But the spins are never zero. It's not a paramagnetic. It's a random order paramagnetic. You always have spins. And then the beauty is that this spin, if you consider you have a strong spin-orbit coupling due to the d orbitals of the ruthenium, then the cavity doesn't couple to the spin directly, couples through the spin-orbit coupling. Why I'm telling you that? Because this is a wide bandgap insulator. You can project that Hamiltonian into a Heisenberg-like Hamiltonian, which is extremely easy to solve. And then you can get that the hopping and the change integrals are proportional to the light-matter coupling. Then you have an analytic model that is what everybody, I don't know if I have it here, has put in the phase diagram of ruthenium trichloride. That is this thing, that you have the zigzag order, the ferromagnetic, which is very close to the zigzag, that's where you live. You can go to the stripe order, what people want to do always, which is you go to this QEDFT quantum spin liquid. Okay, that's what the people want to do since ages. And no one has reached this yet. Then what we have reached is that you are able to move this from here to here with the cavity. And this is really nice because you can compute all the hoppings analytically. And the trick comes because it's this spin orbit coupling and you have a wide bandgap insulator. And you assume dipole and the first order and second order, and then you get the J and the K analytic. And then you end up in a 4x4 Hamiltonian that allows you to solve. And then if you look to the Hilbert space, as I will not show you everything, this is what I told you of the going from the zigzag to the ferro. Depending on the light matter coupling, you can get close to the other side of the quantum spin liquid, but you don't reach it, which is here is the light matter coupling. And here is basically the correlation function. But then what we did, just to give you, we did the pump the cavity. What I told you that is interesting. And then what you do is you follow. You go from the zigzag. This time you go from the zigzag to the 120 order, to the ferro, and then to the quantum spin liquid. However, the region of the quantum spin liquid, just to give you numbers, because it's completely unrealistic. You have to pump 3 eV and have light matter couplings of 0.4. This is out of any realistic experimental realization. Then it's always good to stay in this regime, lower, and then it's more difficult to conclude that we have a perfect access to the quantum spin liquid. But the other case, which is the one that you were asking, which was this one, from the ferro, from the zigzag to the ferro, is really beautiful going from this to this as you increase the light matter coupling. And if you just take I have it there, I'll show you in a minute, it's only the QEDFT model, and then you see where ruthenium trichloride lies. And by the way, this is not only for ruthenium trichloride, nickel iodide, chromium iodide, all the 2D magnets that are being proposed, they are around that energy, that place. And then you plot J over K, which is the change light coupling, and you see that you can modulate it. It's what you've been teaching in model Hamiltonians for many years, that you now have the knob to move it, okay, not a lot, but a little bit close to that value.
Yeah, before I want to ask something, and then probably we'll have a last one. We have refreshments in the Chiostra, and then you were mentioning that you can couple your method with couple cluster or CI, meaning single reference, multi-reference methods. But I am a quantum chemist, and then I understand that DFT is much easier from that point of view. And then my question is it necessary to go beyond DFT, in your opinion, and in case when?
Okay. We did it with Henry Koch, that was here. Okay. No, I think there are some cases in which, let's say, if you have physics-solved molecules on surfaces, that you need to go beyond DFT. For example, if you put water on graphene or water on benzene, standard density functional methods give you the molecule is not physics-solved, it's completely dissolved, whereas in couple cluster, you get a small binding. And then what we did in that case is when you put it in the cavity, you can make that binding disappearing. Then it's always physics-solved. But then we have to do it with couple cluster. For most of the things I told you, couple cluster is doing nothing. I was chosen the cases in which this was clear, no? But even for ruthenium trichloride, I did forget, but what we did is not DMFT, density DFT plus U plus V, which is something we can compute with a standard DFT, and we get perfect electronic structure. It's a Mott insulator, and we get it perfectly in DFT.
So even less multi-reference you would need. This is what you think.
Yes. However, I believe that if you want to monitor a chemical reaction, real chemical reaction, and you want to follow it from the initial state to the transitional state, and the transitional state is open shell system, a radical, I think we are bound to make
because you have the DL Zalder that from that point of view, probably is easier.
Yeah, it's what I told you. I have chosen the ones that...
I understand if you want to have photochemistry in the cavity, then you must do that, but probably this is something that... But what kind of accuracy you need in order to be, comparable with the experiments? Because also this is something else that in general guides us when choosing a method.
At this point, we are not at the level of accuracy, we are at the level of phenomenological aspect, is whether the effect is happening or not. Then this is what something Marco can tell, I think. At this point, I don't think we are going to predict that. Even the TC I told you is indicative. Most likely in the experiments, if they get 1-2 Kelvin, they will be more than happy. But if they get even more, will be a surprise. No, but still, whether there is a change. I mean, we need to first demonstrate that we do change the state. So far, the only clean data we have on that is on the 2D homogeneous electron gas by Jerome Feist. This is the cleanest thing of the data that you see coupling with the cavity modes. Not the way you want it on an aspect, but you do see an effect. But in the rest of the 2D materials, unless you do pumping, you do put an exciton and you couple the exciton to the cavity, which is polariton physics. In that case, there are many effects. There's even exciton polariton condensates. And I'm not denying that. It's whether we want to get an excitonic insulator in the ground state or other type of phenomena in the ground state. That's the whole idea of this. And I believe the magnetic systems are ideal for that. But maybe I'm wrong, because I think would be easy.
Magnetic always is challenging.
I know it's challenging.
That's why it's nice, very nice. I like magnetic field. Everybody knows that I like.
And then you can put
chirality is something else. This is very...
You have all these chiral molecules with enantiomers. Then
because you can guide the chemical reactions in the way that you want, and this is something that I completely understand.
If some of you is bio, or one thing which would be extremely interesting is hemoglobin. I don't know if you all know how, maybe you know that hemoglobin, the way it works is that you have a high spin and low spin configuration, and one carries the oxygen and the other delivers the oxygen. And this happens because iron moves up and down of a planar molecule. Then you could control the oxygen absorption and delivery by controlling the environment. This is well known and is one of the problems of many of the sickness that people has with hemoglobin. But it's a really sensitive thing with connected to high spin and low spin configuration of the hemoglobin, which has been a pain even for CI and coupled cluster to compute. DFT doesn't give it, then I didn't show you.
Yeah, the problem is CI for hemoglobin is far from being trivial. Probably in the exascale.
And then you put in the blood.
Okay, so I think that, we have refreshments now in Chiostra, so follow the locals, they know where to go. You can go on and ask more questions to Professor Rubio. Thanks again.